So Scotty, WA2DFI, is the president of Tapper, and he is also the lead engineer of our Tangerine SDR. Take it away, Scotty.
All right, thank you, Nathaniel. And I hold the record for the most number of slides in the least amount of time. So if you fall asleep, it's not my fault. And Bruce Perrins is number 2, so we duke it out. Okay. So what is the Tangerine SDR project? Well, it's the hardware piece to the Personal Space Weather Station, and it's modular and open source, and hardware and software platform, and for development of it's a bunch of components that we put together to build the software-defined radio. It's also a group of volunteers doing most of the work, and we're building a nice pool of open source software developers. As Nathaniel said, we've got lots of universities working on this, lots of help, so it's good. If you remember OpenHPSDR, anybody remember that project? Kind of like that, but it's kind of like that on steroids. And we'd like to thank National Science Foundation and ARDC for their generous grant, especially ARDC, helped us get around a lot of the trouble we had with sourcing components these days, which is, as you know, can be pretty difficult, but helped us move along on it. Anyway, so Tangerine SDR, what features does it have? Well, first it has numerous uses. So HamSci came to us, 4 years ago now, Nathaniel? And said that they wanted help building a radio because they're smart scientists, and they figured, maybe erroneously, but they figured we were smart radio guys. So they came to us and said, can you help us? And so we thought, well, this will be easy. We'll just go out on the internet, we'll search, and we'll find one that'll work. And we got on the internet, and we searched, and we searched, and we searched, and we couldn't find anything that met the price point and the criteria necessary to satisfy the HamSci requirements. So we said, well, what do hams do when you can't find it? Build it yourself. So that's what we decided to do. And we took all of the information we gathered from all of the other SDRs and said, well, we're going to pick the things that we like the best, and we're going to add a few new things of our own, and we're going to come up with a new solution. And the modular is wherever it is. That's the name of the game today, because we wanted to be able to not only satisfy HamSci, but any other comers like hams, HF guys, experimenters, lots of different users. So here's a few examples. HamSci is up at the top. Did that work? I can't see it over there, so. Okay, so Phase 4 satellite ground station, perhaps you could use it for that. Academic uses certainly, and I know I kind of say, how many people know what the red pitaya is? Well, if we can be better than the red pitaya and cheaper than the red pitaya, then we've succeeded. And so there'll be a version that will be cheaper. There'll be a version that will be more expensive too, but it will do a lot more. So more on what a Tangerine SDR is. Here's the user benefits. Web interface is one of them, so it's really easy. So how many have tried to hook up their SDR 1000 and beat their head against the wall for days trying to get it to work? So the idea is to make it easy to configure. And we would like to build in some whisper and reverse beacon network and FT8 features, so that if you want to play Space Weather Station, you can do that, but you can also play ham radio at the same time. And one of the cool things that Bill has put in his software is the ability to monitor. Since we're direct sampling, we sample all the bands at once, so you can theoretically listen to all of the FT8 signals in the frequency range 2 to 30 megahertz at the same time. And you can put a call in at a station you want to find on the air, and the Raspberry Pi will send you an email when you hear them on. So you want to hear your buddy Bob, right, Bob? Send you an email and say, Bob's on 30 meters right now. You can go work on FT8. Or maybe you know that Bob's on 30 meters, so you go to 20 to make sure that he can't find you. But if he has one of these, he's going to find you, so look out. Okay, hardware features, FPGA-based direct sampling. We use gigabit Ethernet to hook to the computer. not USB, it's gigabit Ethernet. Full coverage from 100 kilohertz to 60 megahertz, since we're direct sampling. Web-based configuration, and the idea is that the computer, especially if you're using a Raspberry Pi or some relatively small computer, is not going to be able to process all of the data at the same time, regardless of what Phil Carnes says. You can tell him I said that. And so you may want to listen to small slices. You probably will. And actually, for the personal space weather station, you might want to monitor 7 megahertz and 14 and 20 and 50 to see when 6 meters opens, things like that. So the idea is that the hardware will slice out pieces of the band and send them to your computer so that you can demodulate small narrowband segments and multiple ones. We're aiming for 8 slices. We'll see how we do. And receive only right now, but transmit is definitely in our future. So these are the components. I'm going to go pretty fast here because I don't want to dwell too much on it. If you want more information, come by the Tapper booth. We're in Building 5, and I can explain to you at whatever length you desire. And we have some sample boards that you can take a look at too. But this is a block diagram. So we have 2 RF modules up here, a clock module here, and we have a leaf I/O module. This is low-speed I/O for things like PTT and key inputs. And then we have high-speed interfaces down here, a dual gigabit port, a gigabit switch, 2 ports, one to go to the Raspberry Pi or other computer, depending on how much horsepower you need, and the other one to your home network, local network. And then just for fun, USB 3 and USB 2. USB 2 is, I put it on there because the part's cheap, okay? So you gotta, and you can plug a DVB dongle in that you can buy for $20 and maybe do some interesting things that you can't do on a Raspberry Pi when you plug it in. So we'll see how that goes. So this part is, we're using Altera Max 10 FPGA, 50,000 logic elements. Now, everybody know what an FPGA is? Because you all went to the SDR forum yesterday, right? Okay, an FPGA is a field programmable gate array. It's basically a sea of logic on top of an interconnect matrix. So imagine in the old days when you put ICs down and connect them with copper, well, there's thousands of ICs in this part connected with traces that you can program. So you can make anything you want inside this FPGA, and there's 50,000 logic elements. So there's a lot of them. In fact, there's enough of them to make a microprocessor, or state machines, or an Ethernet controller, or all kind of things. And some memories for data buffering and to store multiple FPGA images, so in case you want to have images that do different things, you'll be able to load them both onto the board and switch rapidly between them. So main claim to fame is dual gigabit Ethernet ports, allowing you to connect to a local computer and the local network without having to have your own switch. And this is the layout of the, oh, I like that on the left there, Tangerine SDR data engine. It's the Tangerine SDR data engine. I'll fix that later. Anyway, so this is the layout. This is 4 inches square. So if you can imagine a board, about like a CubeSat board. And the FPGA being here, the leaf board, the low-speed I/O is up here, the clock module is down here. And on the down here are the slots for 2 RF modules that go on the back behind the board. Okay, the RF module's next. Let me go over quick. It's a dual 14-bit ADC at 122 megasamples per second, and a 20-bit amplifier, low noise amplifier, and there's a whole bunch of other features useful for customization. Like we have a slot for instance, a high-pass filter in case you live right next door to the broadcast station that's beaming your way. KMIK in Phoenix, the nighttime pattern aimed at my house. Right, you could hear it on your fillings. It was 50,000 watts, nighttime too. So this is a block diagram. You can see from right to left, 2 input channels, and it's synchronous channels, synchronously sampled channels, and the 140-pin connector going to the FPGA is on the left. And there is a real board. We have a real board. Come by and see it in person at the Tapper booth. With the, that's not an orange solder mask, that's Tangerine. Okay. I tried to give them a Pantone number for the color we wanted, but they wouldn't take it. So now the clock module is next. The reason we need a special clock module is because if you are going to network a whole bunch of these all around the world, the data that you collect has got to be correlated between the units somehow. And the somehow is you're going to timestamp the data. So we need a very accurate timestamp. And the clock module is a GPS disciplined oscillator and a timestamp, ability to timestamp the data with a timestamp down to 100 nanoseconds across the world, 100 nanoseconds. Well, we're going to try. We'll see how close we get. Anyway, start with a very stable TCXO, that's a temperature compensated oscillator, and then use the GPS to discipline it so you get down to, and I think John did a whole presentation yesterday on this, but I think we're down to 1 part in 10 to the minus 13 for frequency accuracy. And what we're going to do too is we're going to take, since it's modular, this is a plug-in board. In fact, I'll get to that in just a second. But you'll be able to plug this onto a carrier board that we're making now, or we're working on, that will turn it into a lab-grade instrument for your shack. So you'll get multiple outputs, and they'll all be synchronized to GPS. And it's a synthesizer, so you can program the frequency on each of the 10 outputs. And we have the ability to use higher performance, mid performance, or low performance, or as John Ackerman, our marketing director, says, bronze, silver, and gold levels. And so depending on how much you want to spend, you can get more accuracy or more features. This is the block diagram of the clock module. And there's a picture of it. And what you don't see is on the back side behind here is the footprint for the other 2 low-cost GPSs. So we can manufacture the same board with 1 of 3 GPSs on it, depending on how much money we think you have. Okay, the leaf module, I really don't want to dwell on this. This is just low-speed I/O. What we did is we took the Raspberry Pi hat and we extended the board down. We put an M.2 connector, which is the same as an SSD, and we put high-speed I/O on that connector. So now you've got a Raspberry Pi, which is basically serial port and I2C ports, and now we have 4 LVDS pairs of high-speed data. So you can actually put something significant on a leaf board. And there's a guy already working on a leaf module to do a DLF receiver. How long do I have? I'm done? Okay. I guess I'm done. Anyway, come see us at the Tapper booth right next to the HamSci booth, and I'll run the rest of the presentation for you. There's only a few more slides, but I got to get on before I get the hook.
Thank you so much, Scotty. Next up, while Diego's coming up, do we have a question?